Right, we're going to talk about something called a moment generating function. But before we do, we have to define what a moment is. We've seen moments before. The nth moment of a random variable x is the expectation of x to the n. The nth central moment of x is the expectation of x minus the mean of x, or expectation of x, to the nth power. So this is central because you've moved the random variable, so this random variable x minus ex has mean 0. Right? This variable here has mean 0. So you've basically just shifted the random variable to make a random variable with mean 0. So the first moment is the expected value, ex. The second central moment is the variance. That was the first equation you had for variance. So we might wonder why moments are important. Well, in analysis or calculus, power series are important. They're a very good way to approximate functions. Moments are in probability kind of like what power series are in analysis. All right, so here's the key concept we're going to talk about in this video, moment generating function. It's not the expectation of x to the n, it's the expectation of the exponential of sx. Now this is considered as a function of s, and s is a parameter. S is a parameter. Okay. So we say the moment generating function of x exists if there's a constant a such that this value, this expectation, is finite for all s in this interval from minus a to a. Okay. So you might wonder, why are we introducing this strange thing? And there are reasons. There are actually quite a lot of reasons, many of them theoretical, so you might not quite be able to really appreciate them now, but they are very important, very, very key concept in some proofs. Moment generating functions can be used to calculate the moments. They can solve some counting and combinatorial problems. They can characterize the distribution of sum of independent random variables. We saw just now that to compute the density of a sum of independent random variables is not easy, but with moment generating function, it's quite easy. Okay. All right. They also provide tools for dealing with distributions of some random number of independent random variables. They play a central role in studying branching processes, which I don't know anything about. They play a key role in large deviations theory, which we may say something about later. They provide a bridge between complex analysis, and they provide powerful tools for proving limit theorems. So you see there's a lot of theoretical reasons for really thinking that these are very important. All right, and in the book he reiterates some of these reasons. Okay. He says in particular for us, we'll be using it to work with sums of several independent random variables. Okay. Now, the first application of the moment generating function is finding all the moments. If you know the moment generating function, you can easily find all the moments. And you do that using Taylor series. This is a common Taylor series that you've seen in calculus. Now, never mind that this is a random variable. You can still do this because random variable is just an experiment that takes particular values. So whenever it takes a value, you can take the power series, and we can write it this way. All right. Now, to obtain the kth moment, we can take, remember that the expectation of this is equal to the moment generating function. And the expectation of this here is this sum. We've seen before that when you take the expectation of a sum, you can take the sum outside and put the expectation inside. So the expectation of this sum, I can bring the expectation inside the sum and make it apply simply to the x to the k, because there's no other random variable here. Okay. All right, now here are the moments. And you can just use the formula for the Taylor series coefficients. If you take the kth derivative of this power series, Well, let's take the k. He used k here and he used k here. That's a little bit Bush League, but let's call this L, or let's call this L. Okay. If you take the Lth derivative, then all the terms where k is less than L are going to differentiate out to 0. If you take the Lth term itself, you're going to get expectation of x to the L. And then when you take L derivatives of s to the L, you're going to get L factorial. So you get L factorial divided by L factorial, which gives you 1, so you just get expectation of x to the L, which is exactly the moment here. So if you have the moment generating function and you want the second moment, you differentiate it twice with respect to s and set s equal to 0. All right, now, here's a theorem I'm not going to say that much about, but it just says that if you have two random variables and their MGFs agree on an interval, then in fact they have the same CDF for all t. So they only need to agree on an interval, but if they agree on an interval, then they're the same for all real values. Right. Now it turns out that if you have independent random variables, the moment generating function of the sum of those random variables is equal to the product of the moment generating functions. And that's actually quite easy to prove. The moment generating function of the sum is equal to, this moment generating function is equal to the expectation of the exponential of x1 plus ... plus xn times s. All right, now, if you know that your sum rules, that's the same as the expectation of e to the x1s times e to the x2s times ... times e to the xns. Okay. Now, since x1, x2, xn are independent, we can actually write this expectation of the product as the product of the expectations. So we get expectation of e to the x1s times expectation of e to the x2s, and so on. And that's just the right-hand side here. Now, if I just a little bit, the fact that x1 is independent means that e to the x1 is independent from x2. Okay, the fact that x1 and x2 are independent means that e to the x1 and e to the x2s are independent. But that's, if you look at that a little bit, you see that that's true as well. Okay. Now, the moment generating function does not exist for all random variables. The reason is when you have an exponential, then this exponential goes rapidly to infinity as s goes to infinity, so it may not be well behaved. Now, there's an alternative. Instead of taking e to the sx, you can take e to the jwx. Now, he uses j instead of I. This is engineer's way of writing the square root of -1. So you should get used to that. This tells right away, if a mathematician sees this, we can know that this guy's an engineer. Okay, let me just say something, is that e to the jws x, this is very closely related to Fourier transform. I'm just going to throw out some words here. And this e to the sx, this is very closely related to the Laplace transform. Now, both Fourier transforms and Laplace transforms can be used to solve differential equations. So there's some deep connections here that I'm not going to go into, but you may have seen Fourier transforms, or you can just keep that in mind when you next see Fourier transforms. In a way, you can think of this characteristic function as the Fourier transform of a random variable. Okay. So since this is so similar to a moment generating function, it has similar properties, we could use the very same proof to show that the characteristic function of the sum of independent random variables is the product of the characteristic functions. Okay, so you can see the only difference between this and the moment generating function is this complex exponential. S has been changed into j omega. If you want to say I omega, that's fine. Okay, so let's stop there.